Good morning, everyone. I'm Chin Cao from Stony Brook University. Today, I'm going to talk about DeQA, on-device question answering. This is a joint work with Noya, Niranjan, and Aruna. So why is on-device question answering useful? Imagine a scenario like this. Mateo is looking for medication for his diabetic son. He has gathered the suggestions from his friends on social media. He has also browsed vendor websites for drug information. More importantly, he has discussed with his son's physician over email. Now, when Mateo is in the pharmacy, he needs the answers to the following questions. First one, what's the price of the drug I found earlier on the website? Did my friends give some alternative drugs? And did the doctor say any restriction of the drug? To answer these questions, we need to search through all the data access from the device across multiple apps. We call this device-wide question answering. Unfortunately, there's no support for device today. Either Mateo can open each app on his phone, and then he can use the QA service if the app provides one. This is too burdensome for him. Or Mateo has to send the entire device data on the device, everything he has access across multiple apps to a cloud provider. Then he can use a personal assistant like Siri or Google Assistant to answer these questions. There's a huge privacy risk. Our solution is to develop an on-device question answering system. When the user interacts across multiple apps, the data is stored locally on the device. We then build a QA system over this local data. Specifically, our on-device QA will first build an index and then answer questions completely locally. In fact, you don't even need internet access to answer these questions. So the problem is that building such an on-device question answering system for a mobile device is challenging. State-of-the-art QA systems all use deep learning techniques. So this figure shows the top QA models on the SQuAD leaderboard. SQuAD is a question answering dataset that researchers can evaluate their QA models' performance. All the top QA models are using deep learning techniques, which are very good at modeling text and are widely adopted for QA tasks. So here are some example model architectures. And these models are and complex. These complex models are designed to run cloud. The problem is that we cannot even load any top system on a mobile device today as is, because it doesn't fit into memory. And due to the requirement, it runs extremely slow. In this work, I present DeQA, a system that stands for on-device QA. I will first describe the measurement study we conducted of the state-of-the-art QA models to learn the existing QA model bottlenecks. I will then describe latency and the memory optimizations, and finally, the evaluation of DeQA. So before we discuss the measurement study, let me first explain the QA pipeline. Usually, question answering work as follows. There's a large data collection of documents. This can be Wikipedia, which is widely used in the QA community, or it can be personal cross-application documents that we are envisioning for device-wide QA. The goal of a QA is to return an answer phrase from the data collection in response to a question. Usually, the QA has two stages. The first stage is the search engine, and second one is the QA model. Let me give you an example. Let's say you have a question. When did the Second World War end? The search engine will first transform the question into a set of keywords and then retrieve top relevant documents in the data collection. In the second stage, the QA system runs complex QA models on top of documents. As mentioned before, the state-of-the-art QA models are using deep learning techniques. The QA model to use the information from the question and documents. So the first step is to represent the words in them as embeddings. Embeddings are used to represent words in the sense that words with similar usages and meaning are in the same vector space. Then these embeddings are used as the input to the neural encoding layers to further represent the documents and questions. Then the QA model representation find the answers, score them, and then return the final answer. Now, in the measurement study, our goal is to understand the bottlenecks in diverse QA models. We specifically choose 3 top QA models out of 20 on the squad leaderboard as of September 2018. So these 3 models are representative in the sense that they have very different neural architectures and can cover most QA design choices. Although they have many different model architectures, they all share the same common pipeline we talked about in the previous slide. For the initial measurement study, we used the Wikipedia collection. We tested 2 QA datasets that are widely used in the NLP community. The QA datasets consist of questions and answer phrase and ground truth answer phrase. In the evaluation, we also tested personal datasets. We ran the QA on 2 high-end mobile devices, a desktop PC, and the cloud. In fact, the QA system cannot even run on a smartphone as is due to limited available memory. So we designed memory optimizations that I'm going to talk about later. Once they can run on the devices, let's look at the latency numbers. All 3 QA models take much longer on the smartphone compared to the cloud server. So the x-axis in the figure shows different devices, and the y-axis is the time taken to answer a question. The higher the work, it only takes a few hundred milliseconds, which makes existing QA systems unusable. To study why QA takes such a long time on the phone, we broke down the time taken to run the QA system into different components. This pie chart shows the latency breakdown for running one QA model, which is RNet, on the TX2 board. You can see clearly that the neural encoding is the bottleneck. It takes up over 50% of the total time. You may also notice that the question encoding takes too much time. This is expected because QA systems often process many documents, where each single document has many more words than a single question. So basically, a lot of documents data are huge computation. Of course, there are many existing deep learning optimizations designed for mobile, especially for vision. However, we found they cannot be directly applied for QA. This is because existing optimizations work for QA. Model size is not the issue. The issue is in the large number of documents the QA model has to process. You can find more details in the paper. Our goal next is to address the challenges, specifically in the QA models, to implement an on-device QA system. We designed a set of latency and memory optimizations for the QA models that significantly reduce memory requirement and the QA latency. We first start with latency optimizations and then describe the memory optimizations. So when we design DeQA, we only want minimal change of the existing QA or even no changes because we want our optimizations to be broadly applicable. This optimization is basically focused on 2 main ideas. First, we need to reduce the amount of documents to be processed, and then we also need to reduce bottlenecks in the QA models. To achieve these goals, we have to solve 2 challenges. The first one is that how to reduce the input documents the QA model has to process. So there is a clear trade-off in reducing the number of documents versus accuracy. Processing more accurate answers, but also means you have to spend more time. Processing fewer documents can help reduce latency, but you end up with less accurate answers. So how about setting a fixed top-line documents for all the questions? However, we've found this fixed choice is suboptimal. So this figure in the center shows how the correct answers are distributed across the top 150 documents on the track dataset. We found that the correct answers are evenly distributed across all ranks. For example, if you only process top 50 documents for all the questions, then you will only get half of the correct answers. However, there are two kinds of questions which does not need, may not need a large number of documents. The first is the easy questions. So these are the models can easily find the model processing more documents. In either case, we can get away with processing only a few, which means documents processing can be stopped early. Based on this intuition, we propose a dynamic early stopping algorithm. So the main idea here is to stream documents through the QA models. After processing a single document, we use an early stopping classifier to make a decision whether we should stop or continue. The features of the early stopping classifier are document relevance scores from the search engine. Also, the answer scores from the QA models and a couple of other features. For example, the duplicate answers, etc. You can find more details in the paper. So the main point I want to make here is that this idea does not require changing the QA models. The second challenge we have is how to address the bottlenecks in the QA models. Recall that in our measurement study, we found that neural encoding of documents is a culprit. Now let's take a closer look at the neural encoding blocks bottleneck. So the time by the user. In contrast, the documents we do have access to the documents beforehand. So when the system is waiting for questions, can we do some pre-computing beforehand? Well, the answer depends on whether the documents encoding depends on the involved question or not. So in all the three models we studied, here is a question encoding. And here is a documents encoding. As you can see, in the lower layers, no connection exists between the question and documents encoding blocks, which means the documents encoding does not depend on the question. So our idea is to pre-calculate offline. When a question comes in, we just need to look at it without having to compute again. Of course, there's a trade-off of storage for energy, for latency. We designed memory optimizations so that deep learning QA models can fit into the phone. Documents are larger blocks that creates memory problem for QA. Instead, we break them down into paragraphs and it turns out to be more efficient and effective. Second, instead of loading the entire index into memory, we partial index so that it can fit in memory and then do the search on that. Finally, instead of loading large word embeddings within the QA models, we converted the word embeddings into a key value database and then perform the on-demand lookup. You can see more details in the paper given the time constraint. In this work, we also evaluate the DeQA optimizations. We evaluate DeQA over 3 data collections. So the first one is full Wikipedia. This is a large open domain dataset that is widely used in the NLP community. We use the same QA datasets as in the measurement study. Recall that we support personalized QA on the device. However, there's no publicly available QA dataset over personal on-device data. So we created 2 QA datasets over personal data. The first one is an email dataset with sample emails from the in-range email dataset, which is publicly available. For the ground truth, we curated 120 question-answer pairs from these emails. The second one is a cross-app dataset. We collected the data from 2 users as they continually use 5 different apps for over 1 week. Similarly, we created 100 QA pairs. We evaluate DeQA by comparing with the baseline of top 3 QA models, which are RNet, MRadar, and QANet. The baseline is a version only with memory optimizations applied so that they can run on the devices. DeQA version does not require change the QA models. We then measure the end-to-end QA latency, accuracy, and the energy of both the baseline and DeQA. Now let's look at the latency results. So this figure shows the latency comparison of DeQA with and without optimizations. over the Wikipedia dataset. Y-axis is the latency. The higher, the worse. You can see that DeQA with optimizations can effectively reduce latency from over 80 seconds to 4 or 6 seconds, which is 16 times speed up for all the 3 models. This also indicates that DeQA optimizations are effective, although different QA models have very online different model architectures. So on the right, we also did the mirror the latency on the cross-app data. DeQA is also able to reduce the latency from over 50 seconds to under 5 seconds, providing 13 times speed up. So the numbers for email dataset is also similar. Next, let's take a look at the QA performance in terms of accuracy. We mirror the accuracy of the accuracy drop of DeQA compared to the original QA models. In this figure on the left, y-axis is the percentage of the accuracy drop. You can see that for all 3 QA models on the Wikipedia, this accuracy drop is within 1%. We also did the same accuracy measurement on the single email app and cross-app data. The accuracy drop is also minimal. We measure the energy consumption of DeQA of answering 10 questions. So in this figure, y-axis is the average energy per question. The unit is joule. You can see that DeQA can, with optimizations, can effectively reduce energy by 9 times. Given time constraints, I will briefly summarize other key results of DeQA. On the MobiSys TX2 board, we can reduce the QA latency from over 20 seconds to under 5 seconds, providing 6 times speed up. And we evaluate individual optimization effectiveness. Each DeQA optimization incrementally gives benefits. The overhead of on-device indexing over cross-app data is minimal in terms of both energy and latency. Now I want to conclude the talk by summarizing the main takeaways of DeQA. First, DeQA is an on-device question answering system that can adapt state-of-the-art QA models to support cross-app QA services. Secondly, DeQA is a set of memory and latency optimizations, which require no change to the existing QA models. Lastly, DeQA can effectively reduce QA latency on the mobile phone from over 1 minute to under 5 seconds. Thank you. I'm happy to take questions.